you already have mesenchymal stem cells in you. Mm-hmm. If you put exosomes in, they will get taken up by cells that do home to the inflammation and carry that message there and turn off the inflammation. So why do I have to take these cells out of your bone marrow just so that I can put them back in when they were already in your bone marrow? So how about I just get the exosomes to your bone marrow and let them deal with the cells without having to rip the patient apart to get them out?
Welcome to the Regenerative Warrior Podcast, Doctor's Edition. One of the fastest growing regenerative medicine and anti-aging podcasts in the world. Each and every Tuesday and Thursday, I talk to the top experts to show doctors how to market, manage, and magnify their practice to help more people and make more money. Each episode is short and to the point without wasting your time with pointless conversation. Learn the skills to be successful without traveling to seminars or paying for expensive consulting fees. Are you ready? Because I am. I'm Dr. Ross Carter, and it's time to start the Regenerative Warrior Podcast now. Two things before we get started. The views expressed by our guests are not necessarily those of Dr. Carter or this podcast. One of our podcast partners has just announced special pricing for our listeners. Wharton's Jelly Allograft for $475 per cc. You heard that right, only $475. White papers are available. This is for a limited time, so act now. Why pay double or triple the price from other providers? To learn more or to order, text your name and the word JELLY, Jelly, to 561-962-1231. Write that down. It's 561-962-1231. On with the show.
My name is Duncan Ross. I am a PhD in immunology as well as biochemistry.
All right, so what I'd really like to talk to you today about is something that's fairly new in the community of the stem cell realm, which would be something you specialize in, which is called exosomes. So first of all, where does that name come from? Do you know?
I do. We have vesicles inside of our cells. And
what are vesicles?
A vesicle is a bubble, you could call it, of fat. So a cell really you can think of as a drop of olive oil. I love this.
Okay.
Yeah. So the consistency of a cell membrane is of that of olive oil. Now it has other structures in it which give it shape and cholesterols and such, but really the fat part of it is just like oil. So if you consider that a stem cell is an olive and a placenta is the olive tree, I have one olive tree and I grow olives and then I sell the olive oil.
Interesting.
So these bubbles of fat that are inside of your cell, that's where things happen. They don't just happen out in water. So those are called endosomes when they're inside of the cell. So when those vesicles move to the end of the cell and move out, then they suddenly become an exosome. And I always had a really hard time understanding how cell signals make it all the way through the body without breaking down. Because, you take a piece of meat and you leave it on the table, it turns brown after a while, right? That's the proteins denaturing. So it's getting cooked even at room temperature. Your body is 98 degrees. Right? It's very hot. So these proteins, and I used to express proteins for a living, and I had to run with those proteins from the incubator to the assay because the protein would break down as soon as it just got to room temperature. Not only that, there are things called proteases which break down proteins as it is. So how is this possible that cells are talking to each other and sending proteins all throughout the circulation and that signal actually gets there? I mean, I just couldn't wrap my mind around it, right?
So you're saying that the cells are talking to each other about what the
whether
conditions...
to grow. So consider what's the center of your body. We always, when we're kids, we think it's the heart, right? Your center of your body are these cells called mesenchymal stem cells or mesenchymal stromal cells. Mm-hmm. And when you're growing, why are they called mesenchymal? Because they're from the mesenchyme, which is the middle of the three tissues in embryogenesis, right? Okay. So think about, what are they doing? Well, they're in the middle. So those edges are concerned with becoming your outside, your inside, your bones. They have a plan, but something has to direct that plan. So the only cell that doesn't do anything but secrete growth factor, I don't want to say the only one, that's incorrect, but a cell that doesn't really do anything but tell other cells to grow is the mesenchymal stem cell. A tubular epithelial cell in the kidney doesn't care what other cells want to do, but it has a mesenchymal stem cell close to it telling it to grow. So as a baby grows, these signals are coming from inside of it, and they're coming from these mesenchymal stem cells.
So the MSCs, the mesenchymal stem cells, are actually coordinating what is actually occurring.
Right.
Okay. So that's why these stem cells are so important.
Right. So when you're growing, they're secreting 300 factors, approximately. 300.
Okay, and these are called what kind of factors?
These are growth factors, anti-inflammatory factors, cytokines, whatever. But let's just consider a typical one.
Okay.
So you only want to grow until you're 20. If you continue growing, you're going to grow too far. So all of our growth factors are turned off by design. So if I just told you that the cell orchestrating everything is the mesenchymal stem cell, that's where these growth factors are turned off in large part, is in these mesenchymal stem cells.
So they stop growing and
when you get older, right? And the older we get, the more these genes close. It's called epigenetics, which is whether a gene is open or not to being used, and we die. But that's not to say that the gene is broken. The gene is still there. We pass it on to our children, right? So the enzyme that I like to use as an example is lactase. We are all supposed to be lactose intolerant when we're older, right? It's only Northern Europeans that are able to drink milk throughout their entire life. But everybody needs to drink milk when they're 3 years old. So this lactase gene, and really an operator, a controller of that lactase gene, gets covered over and forgotten about, and then lactase isn't made anymore, and we can't drink milk. But there's no reason why you couldn't get that lactase gene to start working again if you could open it up. So now pretend that all these other growth factors that we're talking about are that lactase gene. If you can open them back up, they can work. And they can cause growth. And in fact, that's what we're seeing. And that's why we call it regenerative medicine. You can't regenerate unless you have some growth signals. And babies have growth signals, and we don't. The reason our adult regenerative medicine cells do work to an extent is because they're anti-inflammatory. And we need to maintain that throughout our life. As soon as you can't control inflammation, you die. If your bone marrow became inflamed, you would die. So we are able to continue being anti-inflammatory throughout our whole life. And as you know, that suffers as well, which is why we get arthritis and such. But if you take just an anti-inflammatory cell and you put it in a knee that is inflamed, it's going to turn off that inflammation, and then the patient is going to feel better. That doesn't mean you regenerated cartilage. And the Mayo Clinic showed that, in fact. The Mayo Clinic, they did a trial where the patients had pain in both knees, osteoarthritis, and they put bone marrow in only one knee, but both knees got better. Why is that? Because of the anti-inflammatory factors in bone marrow. Bone marrow has many cells that secrete anti-inflammatory factors. In fact, almost every cell you can think of secretes anti-inflammatory cells. That's how we keep our body from being inflamed. Inflammation only starts when you really need it to start, and it takes multiple signals to start.
How did it affect the other knee, though?
Because the bone marrow and the cytokines that the bone marrow was releasing in the knee got into the circulation and went around to the other knee.
So when we inject into a joint, it doesn't just stay in that joint?
Certainly the cytokines don't.
Okay.
The cells might. And so that's what I'm starting to talk about, is that the cells stay there. They're secreting growth factors. How are they secreting them? They're secreting them in these lipid vesicles that we're talking about called exosomes. And that's how they're able to make it through the circulation around to that other knee and turn off the inflammation.
And because they're so small, that's the way they're able to travel easily.
Right.
How that works?
They travel easily, right. And they also, where does inflammation really come from? It comes from the lymph nodes. So if you just injected it right into your skin, they would dissipate down to a lymph node where they would encounter macrophages and other cells of the immune system. And then if those cells were inflamed, they'll pick up the exosomes and it'll turn them off. And then that cell can traffic around.
So an injection of exosomes into a joint doesn't just affect that joint. It can actually turn off the inflammation throughout the body.
That's correct.
Okay. Does it actually cause a signaling of any kind of the mesenchymal cells to create or grow tissue again?
It can do that as well. And it does that. And in fact, I know this because my goal is to have the most data of anyone producing exosomes. So I have cytokine panels, but more importantly, I have messenger RNA sequencing. So one messenger RNA can make thousands of proteins. So if the half-life of a protein, the time it takes for a protein to break down, let's pretend it's 4 hours. The time it takes for the message that creates that protein to break down is 5 days. So if you put the message in, you can make thousands of that 4-hour protein over a period of 5 days and have a much greater effect than if you just put the protein in. In fact, in clinical trials where we know that a protein does something and we've just used that protein and put that protein into the circulation to see if it works, it doesn't work. It never works because the protein breaks down. When you have a protein like a Humira or something like that, that's an antibody. Antibodies are really well folded. They persist for long periods of time. But regular proteins don't persist for that long period of time. So, in the messenger RNA of the exosomes, I can see that there are something called a histone deacetylase.
What is that called?
Histone deacetylase. So the way you actually open DNA is by putting a methyl group on it, a CH2, which is then a CH3, and that's why it's called a methyl group. So that opens up the DNA, and now that DNA can start to be transcribed. So in that case of lactase, like I was saying, if it's closed, you just put a methyl group, a seal group on there, and then it's going to open up and be a methyl group, and then you could actually express that lactase. So I know that's in the exosomes. So I know that the exosomes are changing the gene expression profile of cells. And then that can cause a regenerative effect.
Meaning that it's turning
for a
on
period of time, a short period of time.
Is it turning on the cell to work or do something?
It's allowing it to act like a younger cell, whatever that means.
Okay, so if it's a cartilage type of cell, it could potentially turn on the cells that are making cartilage or creating the cartilage and actually grow new cartilage.
Potentially, and you could have a more cartilage-specific exosome that you could make by manipulating the cells when you're making them.
Okay. Great. Now, when you're using an exosome, you need a substrate or something. Otherwise, it'll go up through the whole body. And would it do that?
It would go through the whole body, and that's why we suggest that you use some kind of a scaffold. PRP is actually a good scaffold, but serum is also a good scaffold. PRP makes me worried in many cases because it's inflammatory. All I really want is the scaffold. So if you could use a PRP kit where you're just actually making the thing congeal and not become concentrated, that is the gold standard of what to put the exosomes in.
When you say a scaffold, what is it you're actually meaning?
A scaffold, so imagine a cell, imagine you just created a hole, and on the edges of that hole are these cells. The cells can't just jump out into midair. They need to be able to grab onto something to go do their walking that they do. So if you don't place that scaffold in there, they can't walk.
It's like some kind of substrate or some kind of
substance, right.
Yeah, okay. So that the exosomes can actually attach themselves to the MSCs. Which one is actually attaching?
MSCs attached to the scaffold. So one thing about the exosomes is, you're right, exosomes don't do anything on their own, but they need cells to do it for them. But the MSCs will move towards the exosomes if they have a scaffold to do it on.
Why do they do that? Why do the MSCs move towards an exosome?
That's how they grow. That's how they grow in culture. They send cytokines out, and then there's a gradient. And where there's a dearth of that gradient, they go to fill it.
What's a dearth?
A lack.
A lack. Okay. I've never heard that word. All right. So when there's a lack of that, they go to fill that area.
Right.
Okay. So the mesenchymal cells can become active and start to create whatever they're supposed to create. So are we taking an exosome to cause a rejuvenation of the cells that are dormant in the body, correct?
Right.
Okay. So when we're using it for a joint condition in this case, do we need to include stem cells from an external source to create new tissue? Or can the stem cells that are already there that may be dormant, can they be reactivated to create tissue?
Well, fortunately, there have been studies, so I don't have to make it up. There's a group that created a chondral defect in a rabbit knee model, and they actually show that if you just shoot the exosomes into the joint, it doesn't heal the defect. If you put the exosomes into the joint with a scaffold, it does heal the defect. So that's what I'm saying, is that there are stem cells in that cartilage. As long as you give them a platform to walk out onto, they will walk out onto it.
Gotcha. Okay, so for joint conditions specifically, you need something in combination with the exosomes to get a scaffold.
And that could be, it could be bone marrow, it could be Wharton's jelly, it could be anything that has some substance to it. But I actually was just speaking to somebody who said that they were injecting Wharton's jelly into their baby, and you can't do that. It's like,
why would you do that?
Why would you do that? Because the baby has cerebral palsy.
Okay.
But, those things are very dangerous, okay? Wharton's jelly is really just ground up umbilical cord tissue. Why would you want to just inject that willy-nilly into your intravenous space, etc.? An exosome is 100 nanometers in size. A cell is 5,000 nanometers in size.
So we're talking...
The scaffolding tissue that's in that Wharton's jelly is probably 30,000 nanometers in size. I mean, it's going to get stuck somewhere that you don't want it to get stuck. An exosome will not.
And potentially cause an embolism.
That's correct.
Okay, so yeah. So when you have an autoimmune condition, you don't want a scaffolding, I assume. Right?
Absolutely not. Right.
Okay, so that's when you can use an exosome independently.
Right.
And how do you get the exosome to go to the area that is a problem, or how does that happen?
Fortunately, and that's why people love mesenchymal stem cells, because they home, right? They move towards inflammation. That is true. But you already have mesenchymal stem cells in you. Mm-hmm. If you put exosomes in, they will get taken up by cells that do home to the inflammation and carry that message there and turn off the inflammation. So why do I have to take these cells out of your bone marrow just so that I can put them back in when they were already in your bone marrow? So how about I just get the exosomes to your bone marrow and let them deal with the cells without having to rip the patient apart to get them out?
So how does that process work then?
Well, they go in, they go to the liver, they go to the lymph nodes.
So that the basic way to do that, you would have to IV the exosomes is basically how you would do that. Okay. So now, are there negative side effects or anything that's been found that is a problem when using exosomes?
The exosomes, they're great, but they're not permanent, and that's wonderful. What I was worried about at the beginning is that by causing growth, I was going to cause cancer. And now recently there's been a lot of work that shows that exosomes from a healthy cell can actually be anti-tumorigenic because they have the proteins in it that are making that normal cell function normally. And some of those proteins are called tumor suppressor proteins. So that's what keeps cells from undergoing dysregulated growth all the time. Anyway, elephants have 40 copies of these genes. Some of them, they have 100 copies. We only have 2. So just like that lactase example I gave you, what if our tumor suppressors get covered over and they're not expressed? Then the cells starts growing in an uncontrolled fashion. So just by putting that controlling gene back in there, the cell stops growing. And that's been demonstrated in myeloid tumors in vitro. There's all kinds of literature on it now if you want to go read it.
Is there a way to activate that mechanism of these? What kind of cells are they? Are they these T helpers, or what kind of cells are they actually, the ones that suppress tumor growth?
The tumor itself. If you put the protein inside of that tumor and tell the normal protein, it's going to stop being abnormal.
Sorry for the interruption again. To find out more about this speaker, become a speaker on our show, have Dr. Carter present at your event or podcast, learn more about coaching, consulting, tissue allografts, exosomes, supplements, legal health, or how to create $1 million business card and dominate your area, we're here to help you. Just text your name and any question to 561-962-1231. Write that down. That's 561-962-1231. Or go to our website at drrosscarter.com to learn more. Don't forget about our current $475 Warden's Jelly special. On with the show.
So, is it contraindicated to use an exosome in someone that currently has any type of cancerous condition at all? Or
I think that needs to be investigated. I think that people around the world are investigating it. I tend to believe, after what I've been reading lately, that you could. I wouldn't do it in somebody who has stage 1 or 2 cancer. They need to be treated as patients typically are. But if you're starting to get to the end and there are no other options, that might be a time to try that.
So now the laws in the States about use of live stem cells has some pretty strict regulations. How does that, or does it, have any effect on the use of exosomes? Is that considered live cell therapy, for example?
It is not, and in fact, the FDA does not regulate cell secretions. Let me give you a thought process, though. We all know about homeopathy, right? Homeopathic medicines, they use the right names of proteins on their box, but they don't have very high concentrations of it, right? So that's why it's minute, 0.001. It's completely ineffective. But I have those same proteins, just a little bit more. So maybe this is homeopathic. I mean, it's not regulated. I think it might fall sort of in that gray area.
Gotcha. So what do you see is the future for exosomes in regenerative medicine? How will it maybe evolve? I mean, you're the leader in this area. What is your future and what excites you about it?
I'm probably the leader in clinical usage of exosomes right now, but there are lots and lots of exosomes coming down the pipeline from major pharmaceutical companies. And they'll all have their own little spin. Some of them come from cardiac cells, some of them are genetically modified. I want to come up with a genetically modified one here in the future for anti-aging purposes. I really believe that we can rewind aging, not just stop it. So there's going to be lots of people doing those types of things.
So instead of going after necessarily a disease process, we're doing it as a prophylactic measure to try to prevent you from getting older and living.
Yeah, I actually filed IP on a more anti-inflammatory exosome. I mean, I haven't made it yet. But that's entirely possible. You know, you can do whatever you want with it.
So if someone was like wanting to get involved in this, they could use it as a wellness protocol and not as a disease condition. I'm going to help treat your cancer or your joint condition or your arthritis or whatever. This could be just like, hey, if you want to keep your body working at its younger self, is really what you're trying to do. You're activating or awakening your own cells that actually created you. Is that kind of actually
that's what you're doing? You're just borrowing some other kid's messages to make you act like a kid for a short period of time. And I really saw that in my face. 3 months ago, I had gotten a sunburn. My face would have looked very leathery and craggly the next day. Lately, I've been treating myself with the exosomes in the face a lot. And I got a sunburn, and the next day my face looked even better than it did the day before because I had caused inflammation and brought cells there, and the exosomes were still functioning.
So this is a solution for sunburn.
It's a prophylactic for sunburn.
I like it. Well, kind of an expensive allergy. But I like that. So the applications for this just seem limitless. I don't know how... But I believe I'd ask you if there was any negative concerns that you had, or is there anything?
I haven't seen any yet. If you Google exosomes, you're going to get nervous because every cell secretes exosomes, and tumor cells secrete even more than normal. So you can get good exosomes and you can get bad exosomes.
How does a normal person know what kind of exosomes they're getting?
Well, I mean, I'm pretty sure we treated around 10,000 people to this point, so with the same donor placenta. So
you can only speak to your exosomes
That's right.
and not anybody else's.
Right.
I'm sure every time there's a financial benefit, everybody jumps on board and
That's right.
pretty much says, hey, I can do this as well.
I saw a company selling fibroblast exosomes.
What is that?
A fibroblast is a skin cell.
Okay.
And they're trying to compete with our product. And, those exosomes have nothing to do with my exosomes. They're entirely different growth factor panels. They may be good for something, but they're not anti-inflammatory.
And that's
the key.
Yeah. So you got to be very careful on the type of exosomes you get. Just like with all the companies that sell maybe a stem cell product, you don't know where it comes from and what the quality is. And
a bunch of people just got bitten by that too because they were contaminated.
Exactly. So that's the scary part of the industry because I think, even any negative thing that happens in the industry hurts everyone because people generalize everything as one group. If there's a scam report about a stem cell company, then all stem cells are negative. Or you've got, other people who say negative things about everything but their own products, which are also not FDA approved.
It's a very good point.
Who that is. Yeah, it's one of those things. So what I don't think I asked you is how do you get exosomes from a cell? You got a little tiny cell. Can you see an exosome?
You cannot see an exosome.
So how do you know it?
Well, you have to buy a very expensive microscope called a nanocyte, and then you can see it.
Okay, so you can't actually see them with specialized equipment.
Correct.
So now do you have to stimulate a cell to release these things?
You can.
Okay, so you can stimulate cells to release exosomes. It's okay. And is that what you do, or do you not have to do it?
I have had every kind of exosome that you can think of in the past. Right now, I'm focusing on one that I can see works well, and I'm just trying to repeat and make sure that I have the same quality product. Like I said, in the future, when I may have the desire or time to go back to making all those special exosomes. But for right now, I just have one.
What I was saying is, how do you get a cell to release its exosomes is what I was saying.
You can do 50 different ways.
Okay. How do you know, like when you're making a portion or a quantity, how do you know how much you got since it's so small and you're not looking at each thing that you're doing? How do you do that?
Well, I originally did that by protein concentration. Now I look at the concentration of exosomes on the nanocyte. I can see them.
You can see them, but how do you know the concentration? How do you know?
It counts them.
It does?
Yeah.
Oh, okay. I didn't know that part.
Yeah. It's exactly like your automatic cell counter, except on a much smaller
Just a smaller scale. So you can know how much is in each of the samples.
Right.
Okay. And then after you get the exosomes, it's the fluid around the cells. Is that accurate? Mm-hmm. But it's not just one cell that you're getting these exosomes from. It's from a large quantity of cells, right? Mm-hmm.
But I get rid of the fluid around them. That's kind of a proprietary word.
That's fine. But what I'm saying is, how many cells are you getting the exosomes from?
So when I was doing regular transplantation like everybody does, stromal vascular fraction and these type of things, there was a company which did clinical trials using third-party mesenchymal stem cells. And in a 70-kilogram adult, they could stop chronic graft versus host disease with 14 million mesenchymal stem cells.
So 14 million,
14 million
the magic number.
Was the magic number for really bad inflammation, right? So I figured, well, the inflammation we're talking about is not nearly that bad. So let's just stick with 7 million. And so for years I treated people with that amount, with the exosomes from that amount of cells.
So you would take 17 million?
7 million.
I'm sorry, 7
It's
million.
equivalent to the amount of exosomes that a 7 million cells would make over 2 days.
So you're taking I don't know, a colony of 7 million?
Right.
Does it come from a colony? Okay.
More or less.
More. A group. A big group of cells. And then you take the so it's really, you're taking it from the concentration of 7 million pure mesenchymal cells, not a mixture of all different types of cells, right?
Right.
Okay, so this is like a pure dose.
Right.
So is the exosome really considered the active ingredient, say, of a stem cell?
Yes.
So we're taking the active ingredient of a concentration.
Because, we've known for a long time, there's something called transwell assays. And you know that if you put a cell in one, and the way a transwell assay works is it just has like a screen door between the cells, so the cells can't touch each other. But the proteins and exosomes can pass through. We've known for a long time that you can suppress or activate cells through that screen. So that is how we knew that's how cells work. That's why I was able to jump to this exosome conclusion, because I knew about those experiments. So it's in the soup. And then now we know what it is in the soup.
So basically, when you're talking to somebody, you can say this is the active ingredient of 7 million pure mesenchymal cells and not the, 100,000
whatever, or endothelial cells or whatever the hell you have in there. So and there are no mesenchymal stem cells in cord blood, period, not one.
There's not?
No, there's hematopoietic stem cells in cord blood.
Okay, which are blood
forming.
But what about bone marrow?
Yeah, sure.
But
bone marrow is bone marrow. Blood is blood. Just because it comes from a baby doesn't mean it's that different than your blood. So cord tissue does have mesenchymal stem cells in it, but cord blood does not.
So cord blood is...
It's just blood. Would you do a blood transplant on a patient and expect him to get better? I mean, maybe if it was young blood, but the point is, you wouldn't take his blood out to put his blood back in, right? You would never do that.
Right. What about younger person's blood?
That would work.
But it's not the stem cells that you're saying.
Right, it's the exosomes. Because mesenchymal stem cells are in their niche. They're attached to stuff. They're not floating around in the circulation. They're attached to the vein, and they're secreting exosomes into the vein. So the exosomes go through the circulation, but the cells do not.
But Wharton's jelly is different in that there is actual...
Wharton's jelly is cord tissue.
Yes.
So there's mesenchymal stem cells in cord tissue. But they're third party.
And the problem with that is there's the DNA of the other person.
Yeah, and they'll get rejected.
Always?
Always. Within hours.
But the patient doesn't necessarily know there's a rejection, right?
No, you might never know. 1 in 100,000 cases could have what's called a superantigen reaction against it.
And what would that be?
A big blow up of a cytokine cascade, because they're really specific for that other person.
You're talking about a lot of inflammation.
Yes.
Okay. But normally, even though they have a rejection of it, it's just they don't see results?
Yeah, they just won't see anything.
So, okay, well, that's kind of scary for the rest of the world that's using all these different placental-based products, right. Even bone marrow or adipose, I guess.
I mean, if they didn't work, I always like to say that if PRP didn't work, I wouldn't be sitting here right now. Everything works to an extent. It's just if you really want to have a repeatable outcome and protocol, you got to know what you've got.
But when you say something works, what does it? It depends on what your outcome is.
Well, but you don't know why it's exactly, and you might not understand why it's working. Maybe that inflammation from the rejection, although as slight as it is, maybe that's what caused the healing.
Because it said, hey, there's a problem
exactly.
here, everybody come and help.
Exactly.
Isn't that the concept with the old style they used to use with the sugar? What is that called?
Prolotherapy?
Prolotherapy. Isn't that the same?
Well, I mean, he who shall go unnamed, his whole patent is based on causing inflammation for regeneration. Okay. I am of the opposite school of thought. I don't want to cause inflammation because I want to get normal regeneration, not fibro regeneration.
Okay, that makes sense. Well, cool. What would you like to say to somebody who's they're interested in this field, they've heard a lot of stuff, and everybody's saying, hey, our stuff is the best, our stuff does this, we've got the best stuff,
And it's all related. And then, nobody really I haven't seen a lot of evidence.
Would it be too much to ask, listen, I don't treat myself as far as my health is concerned. I go to a guy with an MD behind his name,
yes.
Right? And that's who I trust. Why would you listen to anybody who walks through the door that doesn't have a PhD, and not a PhD in English, a PhD in that field? That's all I'm asking for, I've never met a PhD who says the wrong thing. I've met lots of reps that say the wrong thing. So
pretty much all of them?
Right.
Yeah, because, that's another totally different podcast I'm going to do. But what I was going to ask you is, what would you say to a new doctor who's getting involved in this? Maybe what to look out for, or what to look for, or what are some criteria to get started in this arena, because they don't really know where to start. What's the first step? What's step one?
Well, there is a good journal. You should start reading that, and you'll start getting real information that you can trust. We are trying to put together books. That's a good way, because, you have to reference things. I can tell you something, but it's a lot more powerful when I put where you can go read it yourself,
Yes.
And seeing is believing. Sadly, a third of journal articles printed kind of fudge the truth. So you have to be able to look at which lab it is, how they did their experiments, to really believe what they're saying. And that's kind of beyond what most people can do.
Right. And most doctors have no idea what they're starting over, and they're like, okay, I'm really excited about this. Where do I go? What do I start? How do I get knowledge enough to know to talk to a patient about it and know what conditions to treat and all that?
That's why I love these Boston BioLife events, because we all get to sit here and this chat that we're having right now, I've done it 60 times in the last 2 days.
That's true, but not everybody can come to a seminar.
Yes, they can.
Well, not everybody is here.
Right.
You got how much of the regenerative population at an event right now? I mean, very few. And they maybe can just started. They've heard of some sales presentation on the wonders of regenerative medicine, and now they're interested. But how do they know to not hit the landmines? Where's the course of let's go this way? What is that? Do you have any idea or no?
I don't know. Call me.
Call me. Well, let's say they wanted to get involved in exosome therapies.
Oh, I have a good way for you. Talk to your hematologist friend.
I don't have any of those.
You don't have a single hematologist friend?
I can't name one. You're a hematologist originally, right?
I'm bone marrow transplantation.
Yeah, okay. So I don't have a lot of people in that realm that are friends.
Well, you could find one. That's a lot easier than finding a PhD in regenerative medicine, right?
I imagine so. So why would I want to find a hematologist?
Because everything that we talk about is known and has been known in hematology since the 50s.
Right.
And so if you study hematology, you've been reading all of this stuff for your entire formation. And now it's just being applied to regenerative medicine, but it's always been applied to leukemia.
Now, are there protocols that are specific for conditions to treat?
Yeah. Okay. There's lots of different, we have this book chapter. Doug Spiel wrote a book chapter where he put down all the protocols that he uses, and that's very informative. It's a good place for people to start.
Thanks for listening to our podcast. Please subscribe to be notified of all new episodes, and also like and share this to help us grow. To find out more about this speaker, become a speaker on our show, to have Dr. Carter present at your event or podcast, learn more about coaching, consulting, tissue allografts, exosomes, supplements, legal help, or how to create $1 million business card to dominate your local area, we're here to help you. Just text your name and your question to 561-962-1231. Write that down. That's 561-962-1231. Or you can go to our website at drrosscarter.com. That's drrosscarter.com to learn more. Until next time, this is Dr. Ross Carter, signing off.